Some problems that we solve are numeric, where we're given numerical values and expected to find a numerical answer. Others are symbolic, where we're just getting a symbolic expression that has variables in it. I want to talk about how to solve problems that are symbolic and how to avoid some common mistakes. Here's an example problem. Let's take a minute to read it. A uniformly charged half ring of radius r is placed on a non-conducting table. It's found that at a height h above the center of the half ring, the potential is V with respect to zero potential at infinity. How much charge is in the half ring? We're expected to solve this symbolically, that is, using variables rather than numerical values. Sometimes this type of problem can be intimidating, but just imagine that the parameters given had numerical values. If this was the case, you know that these numerical values would be plugged into your final expression to get a numerical answer, and that your final answer shouldn't depend on any values that you weren't given. Well, even in a symbolic problem like this, we're still given values. We just use variables to represent them instead of numbers. Our final answer should be in terms of these given parameters, and perhaps some known constants like pi or epsilon naught. After all, if we knew numbers to plug in for these values, we'd want to get a numerical answer, not some expression that still has unknowns in it. So we will treat these given parameters as known quantities. We're told the radius of the ring is r, the height is h, and the potential is v. If we solve for an expression that only has known quantities in it, we have a meaningful answer. Now, one way students often attack a problem is to look for a formula that contains the parameters that we're trying to find. In this case, that is charge. So we might be tempted to choose the expression for Gauss's law that has a charge in it, without really thinking about whether or not that is appropriate, or if the charge in the expression means the same thing as the charge we're asked to find. Let's say we decided to use this expression for Gauss's law and solve for Q. Never mind that the expression has Q enclosed, which is not necessarily the same thing as Q, the charge on our ring. We could rearrange this to get an expression for Q enclosed. And then, in order to get this in terms of V, which we are given, we might look for another expression with V in it, like this one. Now we have this expression, which may or may not be true, but really is not a meaningful answer to this problem. The expression isn't useful because it requires calculating the gradient of V, but all we have is a value for V at one point. It also suggests we have to integrate over an area. But what area? The problem didn't define an area. This result isn't meaningful because we tried to apply equations such as Gauss's law without understanding what they meant or how they were to be used, and so we didn't use them correctly. After all, this is an expression for some enclosed charge, which is not what we were dealing with in this problem. Let's assume we did a better job of picking an equation to apply to the problem. Let's say we correctly realized we needed to use the expression relating the voltage at a point to the distribution of charges near that point. We might be tempted to try to solve this expression for Q, and then plug in the distance h for the variable r, which is also a distance. If we do this, we've completely ignored the integral in the formula, and the value h that we plugged in is not what r represents in this expression. What we should do before trying to apply any equation to this problem is to draw a diagram and label it with the information given and any coordinates that might be involved. Here's a diagram showing a half ring on a horizontal surface with a point P located at height h above the surface. We have identified a small bit of charge dq, which is the charge that is in the equation. The meaning of r in the equation is the distance from the charge dq to the point P, where we have the electric potential V. The integral means we need to add up all of the bits of charge along our ring. So to do that, we need a coordinate that defines the position of the charge on the ring. We can use theta for that. The amount of charge we have in dq is related to the size of that chunk measured in theta as d theta. We can relate dq to d theta by recognizing that the entire charge of the rod q, which is what we're trying to solve for in this problem, is spread over the entire rod, which subtends an angle of pi. This lets us solve for dq and substitute the results in our integral so that we get an expression in terms of our coordinate theta that we can integrate over theta. We want to go from one side of the rod at theta equals minus pi over 2 to the other side at theta equals plus pi over 2. So those are our limits of integration. This is an integral that we can do. After integrating with respect to theta, we have to evaluate at the upper and lower limits. After a little bit of simplification, we can get a more compact expression. We can cancel the pi's to simplify more. We can rearrange to solve for q, which is what the problem is asking for. Here we go. Now let's just check if this is a meaningful answer or not. 4 and epsilon naught are constants, and v and capital R are known parameters of the problem. But what is little r? The problem does not mention little r. We can see from our diagram that little r is related to the known quantities capital R and h. So let's substitute to get rid of little r. That looks better. This is a meaningful answer because it only depends on the constants and the given parameters. We might be tempted to plug in the numbers that we know, like epsilon naught, but the only reason to plug in numbers is to get a numerical value. We don't have numbers for r, h, or v, so we aren't going to be able to get a numerical value. All this does is give us more work to do, more opportunity to make a mistake, and make our answer harder to interpret. Don't plug in any numerical values unless you can plug in numerical values for all of the parameters and evaluate to get a numerical answer. We might recognize that we solved for a charge, and coulomb is the SI unit of charge, so we insist that our final answer should have units of coulombs. This is a common mistake that students make. Don't do this. It's wrong. If we think about what we'd do if we were given numerical values, each numerical value also has a unit that we can plug in. We can use our calculator to work out the numerical result after we convert units when appropriate. We can rewrite some of the units as necessary, such as a volt is a Newton meter per coulomb. And when we cancel units that are in both the numerator and denominator, we'll be left with the units for our numerical value. Because we wrote in that extra unit of coulomb, we end up with units of coulombs squared, which doesn't make any sense for a charge. Thus, you don't want to write units on an expression. Only put units on numerical values that you plug into the expression. The correct units for the expression will show themselves when you work out the numerical value and cancel units. So for a problem when you are given symbolic values, your best course of action is to just solve for a symbolic expression and make sure that the parameters in your answer are the ones that are given in the problem.